So we now have the pleasure of discussing Newton's third law, the last of his earth-shattering, world-changing laws of motion. And I actually like the standard textbook definition for Newton's third law. It says for every action there is an equal and opposite reaction. So the idea is basically if you push on something, that something is going to push back on you. And we can write this as the force from object A pushing on object B, or pulling, is equal to the negative force of object B pushing back on object A. So equal and opposite given by the negative sign, right? So this is kind of a way of expressing that forces always come in pairs. You can never exert a force on something without that something exerting a force back on you, or vice versa. If it exerts a force on you, you're going to exert a force back on it. This equal part here is very important. That is always, always true. Okay? Doesn't matter if the objects are accelerating in one direction or another, if they're stationary, moving at constant velocity. None of that matters. As long as there is a force between two objects, they are always equal magnitude. Both objects will feel the same magnitude force. And in fact, I don't like to think about it so much as that other things always react and come in pairs, but I like to think about it as there is really only one interaction going on. There's one force that is taking place, and both objects feel that same force, whether they're both being pulled in or pushed apart or whatever. There's one interaction. Alright, let's look at a few examples to talk about. If I have a box sitting on a table, table, don't you love my boxes and tables? If we think about the action-reaction pairs, or the Newton's third law pairs of forces, these forces do not occur on the same free body diagram. So if I have a free body diagram for the box, I would say that there's a normal force from the table. Oops. Back. Force normal. So this is acting on the box, right? The free body diagram describes the forces acting on an object. It doesn't describe what that object does back. So on a separate free body diagram for the table, then you would have the force, you could call it a normal force, I guess, but I'll call it the force of the box pushing down on the table. And this is the force of the table pushing up on the box. If you just have somebody pushing against a wall, a long-armed person, the person pushes on the wall, and the reaction to that is the wall pushes back on the person. If that weren't the case, you would just fall through the wall. The wall has to push back on you. So, you know, if you ever punch somebody in the face, you can validly say their face punched your fist with the exact same force that your fist punched their face. Here's an example. It's a little trickier. If you drop a ball, so we now just have a ball falling through the air here, the force acting on the ball is gravity, right? So the force diagram for the ball, free body diagram, will be gravity. Well, what is the reaction pair to that? Well, if we think about the two objects that are interacting, because all forces involve two objects, gravity isn't an object, that's the force. That's just like saying force of push or force of pull. The two objects that are actually interacting are the ball and planet Earth, if this ball is falling on Earth. So Earth is pulling on the ball with a gravitational force. The ball is actually pulling up on the Earth with a gravitational force. And these forces are the same magnitude. So if the ball has a weight of 1 pound, the ball pulls up on the Earth with 1 pound. Now, 1 pound of force moves the ball a whole lot more than it moves the Earth. But when you're walking, you are pulling on the Earth, or even when you're sitting there, you're pulling on the Earth with a force equal to your weight. So in every case, every force is going to have an action-reaction pair. Let's look at a couple other examples real quick. If you have a couple of cars, say your car breaks down and your buddy's car comes and he's going to push you to the mechanic. And your friend is a crazy physicist, so he ties a bathroom scale onto his bumper and he ties a bathroom scale onto your back bumper. Imagine these are touching. So you're going to be moving this way, and if you're going at a constant speed, let's say, how is your scale reading, I guess this was you, huh? How is your scale reading going to compare to your friend's scale? Well, they're going to be equal for constant velocity motion. Now, what if he hits the gas? So now you're accelerating in that direction. How would these scales, the reading on these scales compare? Well, they're still equal. You are accelerating because the other forces, the friction and drag forces, are less than the push force, but the force between the two objects are still equal. Like I said back here, always equal every single time. Okay. Now what if you hit the brakes? So you're slowing down and now we have an acceleration in this direction. Guess what? Still equal, right? Every single time they're going to be equal, regardless of the motion. One last situation. Let's look at the tug of war. Here is Team Green, and over here we'll have Team Blue, and they are bigger boned people, apparently, than Team Green. And we'll get a rope in there, like a red rope. Tug of war. Alright, so if there was say a spring scale, we haven't really used those, but some kind of scale that you could put in the rope over here that would read the force of tension in the rope. And there's another scale over here that would read the force of tension in the rope on this side, so maybe T1 and T2. You can think of that as reading how hard these guys are pulling, and you can think of this as reading how hard these guys are pulling. Well, just like we saw with the bumper, there is no way that you could get a different reading on this scale as on this scale. Essentially, there's one tension in the rope, and both of you will feel that same tension. So if you're both pulling with the exact same force, always, what determines who wins the tug of war? Well, if we look at the force diagrams, the free body diagrams, for the green team, they're pulling on the rope. Newton's third law says the rope is pulling back. So for their free body diagram, we care about the forces acting on them. Okay, so there's a force of tension this way, pulling them that way. What other forces are acting on them? Well, their feet are in contact with the ground, and it's actually friction. If you were on a frictionless surface, you would lose tug of war. So there's a frictional force, and in this case, let's say that the frictional force is bigger than that tension force. Okay, so we've got friction pushing them that way, tension that way. For the blue team, let's look at what's going on. Big bones, smaller force diagrams though. They have tension also pulling them towards the middle. And just like I mentioned earlier, this tension is equal to this tension. So these two forces are equal. Those are the action-reaction pairs. Again, Newton's third law, force pairs are never on the same force diagram. Okay? Now, their friction, we're going to say, is less than the tension. So this is their friction. So these guys will accelerate to the left, and these guys will accelerate to the left also. So green wins the tug of war in this case, not because they were pulling harder. Actually, what determines the winner is who is pushing harder on the ground, because Newton's third law also says the force with which you push on the ground equals the force with which the ground pushes on you. So we could have another Newton's third law pair of you and the ground pushing back on each other. Okay, over and out.